Just a quick overview of the agenda. We're going to talk about auto-scaling. We're going to talk about something we call make before break internally. And then we're going to talk about what is the context behind this migration and how we actually ended up executing this. So for those who don't know what ClickHouse is, it's an open source column-oriented distributed database. It's an OLAP database. So if you want to store like petabytes of data and kind of do like really fast aggregations and analytical queries on top of them, you can use ClickHouse. It's open source. We also have a cloud version, which our team is also part of managing that cloud. And it's got all the fully managed features, serverless, idling, separation of compute and storage. So what happens here is like we have pods running inside these ClickHouse instances, and these pods are attached to PVCs that have metadata in them. The actual data is stored on object storage, as is the trend these days with fully managed serverless databases. And then we have like a bring your own cloud offering if you don't want data to ever leave your network. So like most people who want to manage like something on Kubernetes, a service, or even a database, we started with like a stateful set, started with our operator, which in turn is managing a stateful set, which in turn is, of course, managing the pods, and they have the PVC attached to them. I'm going to do a lot of context sharing. I'm going to rapidly dump a lot of information here because the background context for the migration is actually a talk I did last year at KubeCon Paris. That's called Fantastic Ordinals. So it's going to go really quickly. So if you if you have trouble following, please check out that talk because in that one I go really in depth about the problem with stateful sets and then how we came about solving those problems, right? So this is just a quick plug for the background context. Okay, so really quickly, auto-scaling. So auto-scaling in general in Kubernetes today requires pod evictions. That's because every time you want to resize a pod, you want to change the requests or the limits, you need to kind of restart the pod itself. And that is done inside our cloud using the autoscaler, right? Which is responsible for evicting the pod, and then a controller is going to go over and then resubmit that pod. In this case, this controller could be a stateful set controller, could be a deployment controller, whatever, right? Or if you're managing bare pods yourself, could also just be your own code. And this is the general high-level architecture of when we do auto-scaling. So we have recommendations. We have user-defined resource limits. For example, you want to have a minimum size or a maximum size. And all that information is going to come in. The auto-scaler is going to react to that information, going to start doing pod evictions. And then what's happening here is that you can see there's a mutating webhook. When the controller actually resubmits that pod, the webhook is going to intercept that pod spec, and it's going to mutate it. And then, for example, let's say the customer decides that, hey, I want to have like a 16 gigabyte pod instead of the 8 one, the webhook is going to be responsible for mutating that pod spec, and then when the pod gets submitted, it's going to come up with the new size, and that's how you do vertical scaling inside. That's how basically the standard VPA also works. Vertical scaling. So the problem is that's all right. So what we want in vertical scaling is we want to have like let's say 3 replicas of one size, and then you want to go to a different size for all of these replicas. And when I say replicas, I'm talking about the database replicas and all. If you're familiar with Postgres or other kind of databases, this is not that kind of a scenario where you have like a primary with replicas following. All of these nodes are equally capable of ingesting data and reading data. That's because it's a multi-master kind of a setup if you want to think about it in that direction. So break-first vertical scaling, this is what's standard today in Kubernetes. That's slow and it's disruptive. What do we mean by break-first? That's because if you maintain a pod disruption budget, in our case, for example, if we have a max unavailable equals 1, you're always going to have to do a rolling restart, right? So the image I showed earlier here, like when the pod eviction is happening, you're not going to evict all of your pods at the same time to do vertical scaling, right? Because otherwise you'll have downtime. So you're going to do it like as safely as possible. You're going to start with one replica. You're going to wait for it to safely terminate all the long-running queries. If you have a backup running on that pod, you're going to get rid of that. And then gradually, you're going to restart all of that. And that process is extremely slow and painful. It's going to put more pressure on the existing replicas, which are suddenly taking a lot more traffic. So if you think about it, the exact moment when you want more capacity is the exact moment where you're taking away capacity because you want to resize. And that's terrible. And actually, we maintain some extra overhead on our pods to combat that extra pressure in terms of CPU and memory. So, by the way, just quickly, why is this possible? Why is this the only way to scale today? That's because of some limitations with stateful sets, and I'm going to refer to the talk I did last year that go really deep into the limitation of stateful sets. So the way to solve this is to do something called make before break, which is very simple, right? You add capacity in terms of like these extra 3 new pods, and then you take away the existing capacity, the old replicas, you just take them away. And that's really fast, right? Because the minute customer wants to have like extra capacity because maybe their utilization is climbing, you can just really quickly add nodes without disrupting anything before. So there's no process of rolling restart that's happening here. It's not going to put any extra pressure. If anything, it's going to give you temporarily even more capacity than you needed. And then you're just going to take away the old replica one. So this is what we wanted to do, and the way we did it was we just implemented multi-stateful set. Because the vanilla stateful set, as I said, has some certain limitations because of the way ordinals work. It cannot do this sort of, so this idea, this very simple idea is not possible today using a single stateful set. So we had to kind of refactor our ClickHouse operator to do multiple stateful sets, and this is how it looks like. So the idea is to have one stateful set for every pod. So before we had a single stateful set, and the transition was actually this, right? So each single stateful set is responsible for managing a pod by itself. And this gives us a lot of control and flexibility. And now we have the capability to do make before break. So this is how it works. So we have 3 stateful sets managing 3 pods. You kind of you do a make operation, which adds a new pod. Which, as you can see, it's a bigger size. You break the existing pod. That one goes away. Right? Very simple idea. But it's not, like I said, not possible with stateful sets. So with all this context, we're going to talk about the migration. Now, what do I mean when I say migration? The problem is we now have 2 different code paths inside our operator, and we have thousands and thousands of production clusters which are still using this old approach, right? So we want to move all of our customers from this approach to this one. And this is the migration that we're talking about. Yeah, and there are some of the requirements of this migration, which is you cannot have downtime. You still want to continue to serve queries. It's an orchestration change, right? You're not, of course, you're in future you want to do make before break, so that's an extra capability that you want to give the customers. But at the same time, downtime was basically unacceptable for us. We need to do some orchestration, some organization, you know, a lot of Excel sheets there, a lot of visibility for our customers, and of course, the database itself is not like, I'm talking about pods as if they're like you seamlessly going in and out, but the database itself was not prepared to be this elastic. So there were a lot of challenges that we encountered along the way. And of course, being able to roll back or even mitigate issues as they come into, while migration is happening for critical customers, that was also like an important requirement for us. So again, the migration itself was also like an MBB style migration, which is you have a single stateful set, which is managing, let's say, 3 replicas. And then you immediately add 3 new replicas as three new stateful sets, right? And then you synchronize all this replicas. So on the sync step, which is basically copying over of the catalog and some database internal operations that are happening. And after the synchronization is complete, you can just break this single stateful set. That goes away, and now you are kind of left with 3 single stateful sets. So you go from the old way of orchestrating to the new one, while at no point in time did you have a downtime. You always had at least 3 replicas available in the cluster, and you were always serving queries. So that's kind of the general idea of how we designed this migration flow. And there were multiple pieces of this puzzle, right? So we like it's not enough. Like this code cannot live inside our Kubernetes operator because it's a one-time operation per cluster, and then it'll just be throwaway code. So we needed to come up with a way to design is to have like sufficient decoupling and then sufficient orchestration as well. So we have an API which is kind of responsible for doing things like setting up your auto-scaling configuration, setting up your idling configuration. We use Temporal. I don't know how many people are familiar with Temporal. Hopefully many of you are. It's an orchestration system that we used to kind of handle these migrations as they happen in batches. And we wrote a custom migration controller which was responsible for doing all the things we couldn't do inside our own operator. So quickly, maintenance, this was a very simple idea that you put a cluster inside maintenance mode where you disable certain operations. So if you think about it, while this migration is happening, while you're adding and removing replicas for this critical operation, you don't want the customer to kind of suddenly decide, oh, I want to scale my cluster, because all those operations are going to be influencing what's happening inside the pods anyway. So you want to disable those operations, but you don't want to disable inserts and selects. So we implemented something we call partial migration, which basically removed our Istio virtual service, and then actually it didn't. That was the only thing it didn't do, right? But it disabled from the auto-scaling and the idling backups perspective. All of those operations were disabled, but the inserts and selects were still running. And like I said, we use temporal. This is a really powerful tool that came in really handy because it gave us durable execution. We had to write a lot of business logic to kind of save the initial state of the cluster, perform the migration, which changes the state itself, and then reset the state after the migration is complete to whatever configuration was before the migration even started. We had to do things like, catch configuration drift. If there's a human intervention that's required, send a notification to Slack, pause the migration while someone on call goes and checks those things. So a lot of those things were made really easy and possible with temporal because of its seamless way to kind of do durable execution. So all the inputs and outputs are preserved, failure detection, retries. You get all of these things basically out of the box. And this is how it looked like. So we had a parent workflow, which is basically like a glorified cron job, if you want to think about it in a simple fashion. It's goes and checks what's happening, what clusters are in maintenance mode, and what clusters are eligible for a migration today. So let's say there are 20 of them today, because you want to do it in small batches. You don't want to do it immediately. You don't want to migrate 1,000 clusters. That's going to cause capacity issues in all of your regions. So every day you select a certain small batch of clusters, go over them, and kick off a child workflow for those clusters. And this workflow is going to basically look at our ClickHouse cluster custom resource. It's going to start reconciling and kick off some migration controller jobs. We're going to go into what migration controller is all about, because that's really the heart of what is doing these migrations. But this is the orchestration, a very high-level orchestration view of how we actually manage these migrations. I'm going to hand it over to Jayme to talk about the controller.
Thank you, Manish. I'm just curious how many people know ClickHouse, if you could put your hands up, because I'm going to be talking about some very ClickHouse-specific things during this. OK, a fair number of people. So yeah, first we'll start with the migration controller and discuss a bit the actual implementation of that and how we did that. So I just want to first highlight that this was a test for ClickHouse in terms of being elastic in its scaling, in terms of being cloud native, adding and removing replicas, as you saw from these examples of make before break. And specifically, two things in ClickHouse. One is what we call syncing the catalog, which you can think of as all your databases and your tables. And the other thing is the actual data. Now, as Manish mentioned in the beginning on our cloud product, that data is in S3, but there is metadata at the time of these migrations, at least in replicated merge tree, that is on a local EBS volume. And if that data is not synced to other replicas before you drop a replica, you could have data loss. In theory, the data is still on S3, but trying to piece together which blobs on S3 off of which customer would be very difficult. And the other thing is it was a test for our implementation of this make before break in our Kubernetes operator. So starting with the requirements, we wanted something simple where we could, for example, add a label to a CR using that temporal workflow, and this migration could start. If needed, we could reverse this process, and we could have two states at the same time. So we have our single STS code path in our operator. We have the multi-STS code path. We wanted to live in both of these states, and ideally not implement backwards compatibility in our operator to be able to reverse this, to handle these two states. And so we came up with the idea to have a second controller, a migration controller, that takes over some of this work. So at a high level, we have a CR that's reconciled by two controllers now, which is an unusual pattern in Kubernetes. So we had a mutex to ensure if there was a reconcile still happening from our regular Kubernetes operator. That finished, and there was only one reconcile happening at a time. And so we have our single stateful set replicas and our multi-stateful set replicas managed in some sense separately. Now, that's not quite true, so I'll give a more honest picture on this one. The way that we actually implemented our migration controller is we embedded the reconciler of our main Kubernetes operator into the migration controller, because a lot of the logic to, for example, add replicas, sync the state of ClickHouse, remove replicas, that's going to be the same in the migration controller. So we actually called those functions from the migration controller and called the operator when needed. But any specific migration logic, we didn't have to pollute our code base in the operator and make it backwards compatible. We could just put all that orchestration and logic into the migration controller. Now, so just to summarize that, we can think of the migration controller as a sort of wrapper controller over our Kubernetes operator with additional logic to orchestrate things. And we can handle all those specific things. So we make, we sync, and we break. And that process with two different single stateful set and multi-stateful set replicas and being able to reverse this process is completely handled by the migration controller. Now, I want to go into some challenges when we actually started to roll this out. We wrote a lot of tests, and we wrote integration tests, unit tests, env tests. We have something internal called stress house. We migrated a lot of internal instances. But when we started to migrate customers, we encountered some interesting issues. So the first one I'll go into is an implementation problem that we had in multi-STS and the way we were implementing this in our Kubernetes operator. So I'm showing you here a 2-replica cluster on the left, and we do a make. We add another 2 replicas on the right. And you see here that the first 2 replicas are in zones A and B, and the new replicas are being put in zones C and C. Now, as many cloud service providers do, we try and maintain a zone balance. We have 3 availability zones, and we want no more than a max queue of 1. Now, currently, this is actually completely valid. You have A, B, C, C. You have 2 replicas in C, but that's not max queue of more than 1, so everything's great. But now, as we've described this process of breaking the old replicas, we have to break the replicas that are in zones A and B. And now you're left with 2 replicas in zones C and C. And now this is what we don't want. So now if zone C goes down, we lose availability. A similar problem happened to us with idling in terms of our zone balance. So as Manish mentioned, we idle clusters that don't have usage, and so they scale down to 0. Now when you unidle those instances, and at the same time, for example, start a migration or do a horizontal scale out, you can have replicas schedule in a zone that at that time is valid, but the replicas that existed prior that have a PVC and are not scheduled, once they are trying to schedule, they won't be able to because now the zone is imbalanced. So how did we fix this? We fixed it in our operator by zone pinning and tracking the zones. It's also possible to solve it in other ways, more Kubernetes ways, you could say, with match label selectors, for example. But with the way our operator is written, this was a convenient way for us to do it. Now I'm going to go into some of the ClickHouse specific issues. So ClickHouse has a nice feature where you can have some external system like Postgres or RabbitMQ or NATS, and you can have a table engine in ClickHouse itself. And at time of creation, it makes a lot of sense for ClickHouse to check that this external system is available when you're trying to create that table. So you try to create a Postgres table engine. ClickHouse checks, can I even reach this Postgres instance that you're trying to create the table from? Now, when you add a replica to ClickHouse and you sync the catalog, it tries to create those tables. And of course, it was unable to because in some cases, the customer no longer has that external service, or perhaps they've just shut it down temporarily. But now it makes a lot less sense to not be able to create that table because you're not really creating it. So this was a problem we encountered with the migrations and something that has made ClickHouse more cloud native and elastic. So these are now secondary create queries that don't throw the same errors and do the same validation because they're not creating the table for the first time, but they're just syncing it to a new replica. Similar but completely internal to ClickHouse, materialized views is a popular feature where you have some source table and some destination table, and you have some trigger that will mutate that data into your destination table. And at the time of creation, again, you want to check that that source table exists. But at some point, someone might delete that source table, but still want the materialized view, which is completely fine. But again, ClickHouse tried to do validation. Does the source table exist when syncing it to a new replica? And that failed. So that kind of made ClickHouse, again, more cloud native. Now, this one's quite interesting. So again, we've got a make before break happening. On the left, we have our old replicas. On the right, we have our new replicas. So we've got our single stateful sets numbered S1 to S3, and we've got our multi-stateful sets M1 to M3. And currently, they're both active, receiving customer inserts. Everything's great. We now are doing the sync step. So we're running a command, system sync replica lightweight, which syncs all the part metadata from the break-in replicas to one of the new replicas. So we see we're running it on M2 in this case, but we're getting all the data synced from S1 to S3, but we're also getting the data synced from M1 and M3 in this case. Now, what's the problem with that? Well, a customer could have continuous inserts, and they could be inserting into M1 and M3 when you run this command. And practically, this command would probably time out, and you'd have to rerun it a bunch of times. In theory, if you had continuous inserts forever, this would be an unbreakable replica. You would never be able to succeed this query, and so you could never finish the sync step. So what did we do? We added a from modifier into ClickHouse. So you can do system sync replica lightweight from, in this case, S1 to S3, which is our single stateful set pods. And now we don't need to wait for those inserts that are going to M1 to M3, because those replicas, they're not going to be dropped now. They're sticking around. Everything's fine. DNS issues. Yes, we had DNS issues in this migration. So ClickHouse has a distributed DDL queue. On-cluster queries go into this. So for example, create table on cluster, create database on cluster, these kinds of queries. And at the time these queries are written, the host names of the replicas available in the cluster are recorded in this queue. So for example, we've got S1 to S3 are recorded in this case. Now let's say it was unfinished on S1, and we then dropped that replica, which is fine because it succeeded on the other two replicas. We don't need it to succeed on all three of them. But now ClickHouse, when it tries to read that query from the queue and execute it, it's unable to resolve S1. That replica doesn't exist anymore because we dropped it. And so this was an issue that we encountered trying to deal with DNS issues. So system table copy. This is something that we actually found late in the game of our migrations. So system tables are a replica local table. There's many of them. You have log tables and non-log tables, and these are used for introspection. So you might want to look at the query log to see your history of queries. You might want to look at the metric log. You can see CPU and memory statistics and other things to see what's going on in your database. Now, these are completely local to the replica, as I said, and the problem is with this make before break pattern, you're actually going to lose those system tables. You'll lose all that history, and many customers use this for observability and general introspection into their cluster. Now, how did we solve this? So for the migrations themselves, we had a stopgap solution where we literally select inserted from the break-in replicas to the new replicas and just copied this data. Obviously, you can imagine this doesn't scale very well, and we couldn't do this when we do this for general auto-scaling purposes in customers' instances. And so the fix for this that we implemented was a new disk type called S3 plain rewritable that moves all this data and metadata onto S3 and allows you to attach these disks. So you effectively do a zero copy attach. So you just attach the disks from the old replicas to the new ones instead of copying this data. So I'm going to end on this idea that migrations are kind of a boring thing, I think, generally, and they're quite hard. And it's something that many, many of us as software engineers have to deal with. A lot of projects of software is you build something new, and then you need to migrate the old thing to this new thing. And I think it's quite challenging, especially if you have thousands of customers, each with their own requirements, and you need to make sure that, for example, if they don't want to migrate on a particular date, even if it's a live migration like we had, there's still concerns. There's your product reputation. What if something goes wrong? So just leaving on that thought. So thank you. If you want to chat to us, we've got a booth. You can come over. If you're interested in learning more, we also have a blog post. And
we're hiring. So if you're interested in working on like the intersection of infrastructure and databases, please come and talk to me.